Today, we will explore a fascinating theory that connects the gravitational influences of planetary alignments to changes in solar activity. This model doesn't just provide an alternative perspective on how our solar system operates. It has also shown significant predictive power for forecasting solar events like flares, coronal mass ejections, and the geomagnetic disturbances that can impact our technological systems on Earth. At its heart, this theory suggests that the key to understanding solar activity lies in how planets align relative to the Sun and in their influence on each other through a concept called Triadic Gravity. To set the stage, let's first consider how gravity is usually understood. Traditional physics, particularly Einstein's theory of relativity, presumes that space itself is like a flexible structure, a fabric that can be warped and curved by individual gravitational masses. In this view, each object, like the Sun or a planet, bends space around it, creating gravitational fields that influence the paths of smaller objects caught within them. But this model depends on a pre-existing field or space that reacts to mass. Our theory doesn't make that presumption at all. Instead, it introduces a concept called triadic gravity. Here, the gravitational fields aren't some pre-existing structure waiting to be influenced. They are instead created directly by interactions within specific groupings of three physical objects, which we call triads. It's the triads themselves that give rise to the gravitational forces, shaping how other objects, like the planets and earthbound observers like ourselves, are influenced. Think of these triads as forming a kind of gravitational framework of their own, where each grouping of three objects plays a part in shaping the system. In the context of our solar system, the most significant triadic system is made up of the Sun, Jupiter, and Saturn, whose combined masses generate the main gravitational field. Unlike the traditional view that treats each object as individually warping space, our theory sees gravity as emerging from the relationships between these triads, with nested interactions creating a layered and hierarchical field. Other planets, like Earth and Venus, exist within nested triads that align within this larger system, creating a cascading hierarchy of gravitational influence. Now, one of the fundamental differences in this approach is how we understand the gravitational constant, a key number in physics that's often thought of as a fixed property across the cosmos. In the traditional view, this constant is sometimes approximated as the ratio of the mass of the universe to its volume, a concept that, frankly, works on a scale so broad, it's like trying to explain the flow of a river by talking about the shape of the continent. What our theory proposes is that this gravitational constant isn't fixed at all, but is specific to each triadic system. The larger the masses within a triad, the stronger the gravitational interactions are within it, allowing us to better understand the gravitational norms that govern our solar system specifically, rather than relying on universal approximations. It's important to understand that while our solar system forms its own triadic relationships between the Sun, its planets, and their moons, it also fits within larger triads at a galactic level. In essence, our local solar gravitational norms are shaped by the triads within the solar system itself, while broader structures like galactic coherence are formed through relationships with nearby stars. So when we look at a triad involving massive objects like the Sun, Jupiter, and Saturn, the gravitational pull is actually stronger than what traditional calculations would predict. This means that during certain alignments of planets, we see amplified gravitational influences that can significantly affect the Sun. Now, why are alignments so important? Well, they represent moments of heightened coherence in the triadic gravitational interactions. And this coherence has measurable effects on the Sun's internal dynamics. There are three key types of alignments that we need to consider: conjunctions, oppositions, and what are known as squares. Each of these configurations has a distinctive way of affecting the Sun. First, let's talk about conjunctions, which occur when multiple planets align on the same side of the Sun. Think of these moments as when planets fall into a line or a very narrow angular range. This grouping acts like a magnifying lens for gravity, drawing on the combined pull of the planets to create an intensified force on the Sun. The tidal forces generated by these conjunctions can cause disturbances deep within the Sun's convective layer, which is responsible for transporting energy from its core to the surface. These disturbances can lead to something known as magnetic reconnection events, where the Sun's magnetic fields snap and realign, releasing vast amounts of energy as solar flares or coronal mass ejections. Historically, significant solar storms and peaks in solar activity, like sunspot maxima, have often occurred during such conjunctions, particularly when involving the major players like Jupiter, Saturn, Venus, and Earth. The more planets that come together in this alignment, and the closer they are to each other, the stronger their combined gravitational influence becomes. Next, we have oppositions. This is when planets line up on opposite sides of the Sun, forming a straight line through it. If conjunctions create a unified pull in one direction, oppositions work differently. They effectively stretch the Sun, pulling it in two opposing directions. The result is that the internal layers of the Sun experience a kind of oscillation, a rhythmic movement within its plasma that can disrupt its magnetic fields. These oscillations often lead to bursts of solar radiation, manifesting as increased solar flare activity. The records back this up. There have been clear peaks in solar flares and geomagnetic storms during times of planetary opposition, especially between the larger planets like Jupiter and Saturn, and even more so when the inner planets such as Earth and Venus are also involved. The third type of alignment to consider is what we call squares, which occur when planets form a right angle relative to the Sun. Squares are particularly interesting because they represent a tensional relationship, introducing perpendicular gravitational influences that place unique stress on the Sun's magnetic structure. Imagine the Sun being pulled in different directions at 90-degree angles. This creates a shearing effect, where the magnetic fields inside the Sun are stressed in a way that can lead to instability. When this tension reaches a tipping point, energy is released in the form of solar flares or coronal mass ejections. These effects are even more pronounced when multiple squares form between various planets and the Sun, creating bursts of solar activity that can have dramatic consequences for Earth, such as intense geomagnetic storms that affect the ionosphere and disrupt communications. But there's a deeper layer to all of this: the idea of superposition. In this context, superposition means that the effects of these planetary alignments don't just happen in isolation. They overlap and amplify one another. When conjunctions, oppositions, and squares occur close together in time, their gravitational influences combine, intensifying the tidal forces acting on the Sun. For example, if there is a conjunction between Jupiter and Saturn, while at the same time Earth and Venus are forming a square, the superposition of these influences can greatly heighten solar activity. This means the potential for large-scale flares or coronal mass ejections increases dramatically. Such periods of superposition, with overlapping planetary alignments, have historically correlated with some of the most significant solar events. One well-documented example is the Carrington event of 1859, which remains one of the most powerful solar storms on record. At that time, notable alignments occurred among the inner planets like Venus and Earth, and the outer giants like Jupiter and Saturn. This storm had a profound impact on Earth's magnetic field, disrupting telegraph systems worldwide and producing auroras seen as far south as the Caribbean. Empirical data across solar cycles also supports the theory. The Sun's 11-year cycle of sunspot activity often reaches its peak during periods when strong planetary alignments occur. These alignments serve as reliable indicators of when to expect solar maxima, and they have been used effectively to develop predictive models that anticipate both the rise and fall of solar activity based on upcoming planetary positions. The real-world implications of this theory are substantial. Periods of heightened solar activity resulting from these alignments are linked to geomagnetic storms on Earth, events that affect our power grids, satellite communications, and even GPS systems. By statistically analyzing historical solar events and correlating them with known planetary alignments, This model identifies patterns that have the power to forecast space weather. It doesn't just provide general warnings, but offers specific probability windows when the likelihood of solar flares or storms is heightened. If a major conjunction between Jupiter, Saturn, and Earth is predicted, along with additional squares forming with Mars or Venus, the model anticipates a surge in solar activity. The practical applications of such forecasts are vital for industries sensitive to space weather. Satellite operators, power grid managers, and aviation sectors can take precautionary measures during these periods to mitigate potential disruptions. And as our dependence on technology grows, the ability to anticipate space weather could prove to be an invaluable tool. In conclusion, this theory on triadic gravity offers a compelling framework for understanding how planetary alignments impact solar activity. By focusing on the interactions within triads, it provides insight into how conjunctions, oppositions, and squares can amplify tidal forces and magnetic stresses in the Sun, triggering solar flares, coronal mass ejections, and geomagnetic storms. Its predictive power lies not in trying to explain every mechanism, but in its ability to correlate these alignments with observed solar phenomena, offering a reliable way to forecast space weather events and protect our increasingly technology-dependent world.